Okay, so optimization, let's start. So this is our compiler. All these slides actually I have taken from a Stanford University course. So this is our compiler. As you know, we give a source code and these are the phases. One by one these phases work on this source code: lexical analysis, syntax analysis, semantic, intermediate generation, and finally we go to intermediate representation optimization. So in this phase we get something called intermediate representation. Okay, some intermediate representation we can use, 3 address code, SSA, something we can use here. So in this phase we get intermediate representation IR and we want to optimize that. Okay, and the motivation for optimization we have already discussed in the last class, so I will just quickly go over this thing. So this is our intermediate representation optimization. And why do we want to do these things? All these things you can already see. So basically improve the intermediate representation generated by the previous stage to take better advantage of the resources. Basically reduce the execution time, reduce the space that is taken, and all these things. This is actually this code optimization is one of the most, actually it is the most, you can say the most important, and it is the most complex part of compiler. As I told you that a disastrous incident that happened, after that incident this has been a very active field of research. Many researchers are working actively, and every after every few days, after every few months, new optimization techniques and better techniques are coming. Anyway, let's see. So why do we do the optimization? This we have seen in the last lecture. You can go through all the slides when I will share these slides. Optimization from the intermediate representation. So for example, let's assume this is your high level code and you transfer it into IR code. So let's assume this is your IR, intermediate representation code. Now you want to optimize this code. Okay, you want to optimize this code. Then so this is your intermediate representation code and you want to optimize it. So what are the optimizations you can perform here? So let's see. For example, you can see that you can see one thing here. What are the optimizations you can perform? Let's see. So T2. So you can see here you are computing something called x plus x. This expression you are computing here. Okay, and you are putting it into T2. Okay, so this expression you are computing, and after that you are putting here, and then actually you are not changing x, you are not changing T2, nothing you are changing. You can see here neither here you are changing. Okay, here also you are not changing. Okay, so you can see finally actually here you don't have to calculate it again. So what you can do, you can replace this with directly T2. This is what only first page you are able to see. Okay. Okay. Wait a second. Is it visible now? Optimization from IR generation. This is the headline. And now the movement is visible. Okay. Okay, so let me just restart what I was saying. So we are looking at this IR optimization. So we have IR code, IR generation. So here in this is after this stage we have something called intermediate representation. either 3 address code. We can use any of the intermediate representations like 3 address code, SSA, something. So you have this intermediate representation. Now you want to optimize it, and the motivation for optimization and why do we optimize, all these things I have already discussed in the last class. And as I told you, there was a disaster happened, and after that this has been a very active area of research. Many researchers are actively doing research in this area, in this code optimization area. So this is a very important area, very complex area, and many algorithms are being developed every year. Okay, so and why do we want to do the optimization? And this motivation we have already seen in the last class. You can go through these slides once I share these slides. Now let's see optimizations from IR generation. So this is your high level code, and let's assume you transfer it into 3 address code and you get this. So this is your intermediate representation. Okay, now you want to optimize this intermediate representation. Then what you can do, what optimizations can you do? Let's see what optimizations can you do. So what are the optimizations that you can do here is that see this what you can do is very simple. So you can replace what it is doing T2 T0. So you see here we are calculating this expression x plus x. This expression we are calculating and we are putting this into T0. You can see after this expression neither we are changing this x nor we are changing this T0. You can see this x, this T0, we are not changing them. You can see neither we are changing them here nor we are changing we are using them, but we are not changing them. So you can see this expression that you calculated and you stored it into T0. Now you don't need to calculate it again. So what you can do here, x plus x, in place of this x plus x you can directly put T0. So you can see this is actually your sub expression elimination, common sub expression elimination technique. We have some techniques. If you have seen the GATE syllabus, then we have some code optimization techniques, and one of them is common sub expression elimination. So this is actually your common sub expression elimination. Don't worry, we will see all these techniques in a very detailed manner. Right now I am just telling you, in this one program I am telling you that many optimizations we can do. So the first optimization is that you are calculating this expression and you are storing this result into T0, and after this and after this you can see, after this first line you can see one thing. After this first line, neither you are changing x nor you are changing T0. You are not changing any of them. So because you are not changing x, you are not changing T0, so this expression you don't have to evaluate again. What you can do here, you can reuse T0. So you don't have to do the addition again. You can save time and you can just put T0 directly. Similarly here also, what you can do, you can put okay, let me I will tell you. See, now this basically you are not evaluating this expression again. So this is called common sub expression elimination. This is a common sub expression and you have eliminated it. Now the another technique that we have, what is the another technique? That is, see here you are assigning this T2 directly T0. This T2 is being assigned the value of T0. Okay, now after this you can see neither T0 is changing nor T2 is changing. After this statement, T2 T0 both are not changing. Okay, so what you can do here, actually what you can do here, you can replace this with T2. Okay, what is the reason? Anyway, first of all, when you were changing this x plus x, you were changing with T0, so you can replace everything with T0. Now this T0 you can replace with T2. This is called copy propagation. Okay, right now don't worry if you don't get it, don't worry, because we will take some simple examples and we will try to see it. Okay, but in this same example we can see all these things, but this is your copy propagation. Okay, so we are basically, because T2 is being assigned the value of T0, so we are replacing this T0 with T2. This is how you can do. Now after this, what are the other things that you can do? So you can do actually many optimizations you can do here, and after you can eliminate some for example, this T2 you can, so okay, let's revisit this example after we are done with the, because this is a complex example, we need algorithm to solve this example. Okay, so let's first go through all the, you can go through this example, what they are doing, you can go through this after the class is over. Just looking at the slides, you can see what is happening here. Basically he's changing this T3, because you can see this y is being assigned to T1. Now you are not changing T1 anywhere, so what you can do here, actually here in place of this y you can assign T1. Now similarly in place of this T3 you can assign T1. So like these are the copy propagation. We will see this is called copy propagation. This is one type of code optimization technique in our syllabus. So okay, let's see all these techniques one by one. So for example, if this is your high level language code, then you can do some optimizations here. What is the optimization that you can do here? You can see this this y plus z you are calculating every time. Like every time the loop is running, you are calculating this y plus z, but actually you don't have to calculate it again and again. You can see inside this loop, this y plus z, this is not changing. So this y and z, these are fixed. So what you can do, you can put it outside the loop so that you can save some time. What you can do, you can put it outside some loop. Maybe you can put t here. Now you can put t here. So you can see these type of things are like will save you a lot of time. Like every time the loop is running, let's assume this loop is running 1000 times, then 1000 times you are doing this addition. You are doing this addition 1000 times unnecessarily. What you can do, you can do this addition only one time, okay, and then you put this t here, so it will save a lot of time. So all these things are actually optimization, different optimization techniques we have. So we will now we will see all the techniques that are in our GATE syllabus. Those techniques we will see. Okay, actually this word that we are using, optimization, actually we should technically see, we should not use this optimization word, because optimization says that basically you are finding a optimal code, but actually finding the optimal code is undecidable problem. Okay, and that's why actually we are using this code optimization, but actually the actual thing that we are doing is code improvement. We are just improving our code. Okay, but because actually this general problem is actually undecidable. Okay, this general problem is undecidable. That's why we should actually, if someone says you that if someone asks you can you find the optimal code, if I give you some IR representation, let's assume if I give you some IR representation, and from that IR representation can you find optimal code, like best optimal code, then this problem is actually undecidable. So what we can do, we can do some improvements, some algorithms we have. Okay, we will see some algorithms like dead code elimination, constant propagation, copy propagation, okay, libeless analysis. Okay, all these things we will see, but these are just some algorithms, and many other algorithms we have, but those are not in the GATE syllabus. But these algorithms will do some improvement anyway. So I just wanted to tell you that this optimization, like getting the optimal code, this is an undecidable problem. Okay, anyway, why this is undecidable on all these things, that is not our area. And so now let's see. So why are we doing the optimization? I told you we want to reduce the runtime, we want to reduce the memory usage and all these things. Now all these concepts we have seen so far. In the last lecture we have already seen these concepts. That's why I am just going very fast, because all these concepts we have already seen. Now now there is a terminology, actually there is a terminology called, if you are doing some analysis, let's assume I give you some program text, I give you, you are analyzing that program text and you want to do some optimization on that text. Okay, so to do the optimization you need to analyze it. Okay, so we say that some analysis is sound if it never asserts any incorrect effect about the program. As I told you, actually this we have already seen in the last class also. This sound means basically an analysis is called sound basically if you are not taking any risk. As I told you in the last class also, बिल्कुल भी रिस्क नहीं लेने का है. तो so actually this let's see this by example. So here you see this value, here you see this, so this is your program. If this is your program, then one thing you can notice, you can see either this value is true or false. So this condition will evaluate true or false. If this condition evaluates true, then x will be 137. So basically either 137 will print or 42 will print, depending on, so you can see either 137 will print or 42 will print, depending on the truth value of this y less than 5. Depending on that, these are the only two possibilities that are there. When you actually run this program, when you actually execute this program, then you will see that either 137 will print or 42 will print. So now my question is, if I say this line, this is my claim, is this claim correct? Tell me, is this claim correct? Is this claim correct? You can see this claim is actually correct. This claim is correct because we are not saying anything false. Like I am not lying. The fact is that I am not lying, basically. That is the point. Here I am saying that at this point in the program, x holds some integer value. Yes, x holds some integer value, either 137 or 42. So yes, my statement is correct. My claim is correct. But of course, my claim is like a very, you can say, useless claim. Because you can see only these two values are possible, but I am saying that some integer value is possible. Then you can see this is some information, like this could be useful information for you. This information, if I tell you that here this x value is either 137 or 42, then this is a useful information for you. But what is this? This is not a useful information. I am just saying that here x is having some integer value, so this is not a useful value. You can see this is less useful information for me. But the thing is, my claim is correct. You can't say that my claim is false. You can't say that my claim is correct. So because I am not asserting anything false, so this is actually sound. This is sound analysis. Sound analysis means you are not saying anything false. That's the only point. You are not saying anything false. That's the point. Now let's see the next example. So this is sound analysis. Let's see this. Is this sound analysis? Is this sound analysis? Is this sound analysis? Yes, this is also sound analysis. This is also precise analysis actually. This is very sound and this is very precise, you can see. Because here x can either have 137 or it can have 42, and our claim is that at this point in the program x is either 137 or 42. So this claim is also true. This claim is better than the previous claim, but remember the previous claim was also sound and this claim is also sound. The previous claim was also true, this claim is also true. Okay, so this is the definition of sound, you can see. An analysis is called sound if it never asserts an incorrect fact about a program. If you never assert an incorrect fact about the program, then that analysis is sound analysis. In the last class also we have seen these type of things. So this is a sound analysis. This is a sound analysis. Is this sound analysis? Wait a second. Actually, this is like this. Okay. Is this sound analysis? Tell me. This is not a sound analysis, because here we are giving false information. Here we are saying that here the value of x will be the value of x will be 137. This is a false information because maybe your x value can be 42. So you are giving false information here. So this is not a sound analysis. Actually, this type of analysis you should not do. So this is not sound analysis. Is this sound analysis? Is this sound analysis? This is also sound analysis. We are not saying anything false. I am saying x is either 137 or 42 or 271. Like, can you prove me false? Can you prove me false? I am not saying anything false. I am saying either 137 or 42 or 271. If you want to prove me false, then you have to give me some other value. Like here the x value, if the x value is 500, then this claim will be false. But right now this claim is true. Are you getting this point? I am saying either 137 or 42 or 271. It's just like here. It's just like here. X holds some integer value. Just like here. But I am not saying anything false. I am saying that x holds some integer value. Yes, x holds some integer value. Similarly here, I am saying x is either 137 or 42 or 271. Yes, my statement, my claim is true. My claim is true because you can check. You can go and check my claim will be true. You will see that value is 42. Yes, my claim is saying that value can be 42. You will see that value can be 137. Yes, my claim is saying that value can be 137. So you can see these are the only two possibilities, and my claim is allowing these possibilities. So my claim is true. This is a sound analysis. Anyone has any doubt in this? This is also sound analysis. Anyone has any doubt in this? Okay, so you can see this is also a sound analysis. Okay, it's like this. Okay, it's like this. If let's assume there is a witness. Okay, and this witness tells the police that I have seen the thief, and the police ask, okay, tell me tell me something about this thief, and this witness says that he is a human being. He is a human being. So of course he is not lying, right? Of course this information is useless. Okay, this information is useless. He is just saying that he is a human being. That's it. But he is not lying. The fact is that he is not lying. Okay, you can't say that he was lying. You can see. So it's like this. Okay, so this is called sound analysis. Now, so remember this soundness. This is actually when you study this optimization and all these things in a formal manner, then these things will keep on coming on. This soundness, preciseness. There are two terminology: sound analysis, precise analysis, and there is something called you can say over analysis, under analysis. And there are many terminology, but I don't think that these things are in the GATE syllabus. But anyway, this is a very simple thing, this sound analysis, because this is important. Right now, these things are not important to us, but this sound analysis is important to us. Basically, don't take any risk. Okay, like here you are not taking any risk. You are giving some more information, but you are not hiding any information. Okay, you are giving some more information. If you are hiding some information, then that is false. If you are saying that here the value will be 137, then that is false, because value can be 42 also. Okay, so anyway, this is your sound analysis, and all the analysis that we do from here onwards, all the analysis that we do in our actually in our complete optimization, whether local optimization or any technique that we study, in all these techniques we do something called sound analysis. Okay, so anyway, now let's see what is syntax preserving optimization. The name itself is telling you syntax preserving means basically the meaning of the sentence should not change. Like it should not happen that you have completely changed the meaning of the sentence, your program. You have just completely changed the meaning of your program. That should not happen. Okay, you can do some optimizations. Like in the last class we saw s equal to 1, s equal to 2, s equal to 3, s equal to 4. These 4 lines were there, and we replaced these 4 statements with this one statement. Because when we do this, then I am not changing any meaning, any semantics of the program. You can see, because anyway these 4 lines are going to do the same thing that is going to be done by this line. So that's why you can see here I am not changing the semantics of the program. So the semantic preserving means basically it does not change the semantics of the original program. For example, what are the examples? For example, these type of things like eliminating unnecessary temporary variables. Okay, eliminating common sub expression like common sub expressions you are removing. Okay, dead code, like dead code elimination. In the last class we have seen dead code elimination, you are removing those things. So those things basically do not change the semantics of the program, so these things are allowed. Okay, like right now, just what we did in the last example, if you remember, there was like this, while x is less than y plus z. So what we did, we took this y plus z and we put it outside the while loop. Why did we do this? Because inside this while loop, this y and z were not changing, so we don't want to compute it again and again every time this while loop runs. So what we can do, we can put it outside, so that we only have to compute it once. So you can see the semantic of the program is not changing if you do these kind of things. Okay, so what are the things that are not allowed? These things are not allowed. If you are completely changing the behavior, if you are completely changing the semantics of the program, that is not allowed. For example, your original program is doing bubble sort, and after optimization you are making it quick sort. This is not allowed. Like your original program is doing, let's assume, bubble sort, okay, and you are changing it into merge sort. No, that is not optimization. That is completely different thing. That is not called optimization. Okay, so so all the optimization that we will see, they will be semantic preserving. The semantic will not change, the meaning will not change, the behavior will not change. Okay, now let's these basic blocks we have already seen. What is a basic block? This you already know, some sequence of instruction, and they should execute atomically. You can see basic block means basically you have sequence of instruction that will execute atomically. They will execute in a group. Okay, all these things we have already seen. The control flow graph, this also we have already seen. Now we have some type of optimizations, something called local optimization, something called global optimization, and something called inter-procedure optimization. Let me tell you what is local optimization. Local optimization means you have a basic block, and inside this basic block you are doing your optimization. Okay, so local optimization means you are doing your optimization inside a single basic block. Inside a single basic block you are doing your optimization. In our GATE syllabus we have local optimization. In GATE syllabus we do not have these things. You can go, you can check the syllabus of GATE, only we have local optimization. So basically you have a basic block, and inside this basic block you are doing your optimization. You are running your optimization techniques, you are running your optimization algorithms inside this basic block. Okay, without worrying about other things, just focus on this basic block. This is called local optimization. Global optimization means you have a CFG, you have many basic blocks, and this is your CFG. Let's assume this is your CFG. Then global optimization means basically on this complete CFG, you are doing the optimization. Means now you are doing the optimization between the blocks, between the basic blocks also. So that is called global optimization. Global optimization means on the entire control flow graph, on the entire CFG, you are doing the optimization. That is called, you are running the optimization techniques on the complete CFG. That is called global optimization. What is inter-procedural? It's like this. Let's assume you have many functions, many procedures you have. For each procedure you make a CFG. Actually we make CFG for each procedure. So for procedure P1 you make a CFG, for procedure P2 you make a CFG. Let's assume in your program you have some procedures. Now you make CFG for each procedure, and you are doing the optimization among these procedures, like CFGs. So among the CFGs you are doing across the CFGs you are doing your optimization, you are applying your optimization techniques. Then that is called inter-procedural optimization. Okay, so these things are not in the syllabus. Only local optimization is there in the syllabus. Means local optimization means inside a basic block we are doing the optimization. Let's see here what is local optimization. So before we proceed, anyone has any doubt right now? Okay, so let's see this local optimization. So local optimization, remember, this is your basic. So from this program you can very easily make this basic block. You can make this CFG very easily. You can make, we have already seen this in the last class, how to make a CFG, how to find leaders and all these things. Like the first statement is always a leader, okay, and the target of the goto and the next statement of the goto both are leaders. For example, if this is the target, then this is a this statement is leader. If this is the next statement, then that is also a leader. I told you, whenever we have conditional goto statement, then we have two successors. Okay, so all these things we have already seen in the last class, how to make CFG, how many basic blocks will be there, how to find basic blocks. So you can just apply the leader algorithm, and number of basic blocks will be equal to number of leaders. And how to make these edges, this also we have seen in the last class. For every conditional goto statement, there will be two edges. Okay, one on the true branch, another on the false branch. And whenever you have unconditional goto, then there will be only one edge. Okay, because that is unconditional goto, so there will be only one edge. All these things we have already seen. Now so local optimization says that inside this basic block, don't worry about these things, don't worry, just inside this basic block do your optimization. So what you will do, you will do optimization inside the basic block. Here what you can do, here you can do something called constant propagation analysis. We will see it right now. I am just letting you know that this analysis is called constant propagation. What we are doing, see, at the compile time, the compiler what it will do, without running the program, because right now we are at the compiler stage, right now we are not running the program, we will run the compiled program. So while the compiler is doing its work, so it will only do the optimization on the static part, means on the text of the program, on that it will do the optimization. So now this compiler is reading your program, and it is coming here, T0 is being assigned the value 137. So you are assigning 137 to T0. Now you are assigning Y T0. So what you can do, you can do something called, here you can replace this with directly 137, because what you are doing, you are assigning this 137 to T0, and you are assigning this T0 to Y. So what you can do, you can replace this T0 with 137. This is called constant propagation. We will see this in the detailed manner after some time, but this is called constant propagation, whatever, propagation. Okay, constant propagation. So this is how we do constant propagation. Now, so what you can do now, basically after this, so you can do this constant propagations. Okay, Y, you can just directly assign this Y equal to 137, and then you can remove this Y, you can remove this, because this will become actually your this will become dead code. This we will see at a later point of time why this becomes a dead code, but you can eliminate it, and this will be your optimization. You can see this is your local optimization. This is how you can do the local optimization. Okay, so now for example, here also you can do the local optimization. Here you are assigning this value Y to T1 and this T1 to Z. So what you can do, you can do something called copy propagation. Copy propagation says that if you are doing like this, you are assigning variable Y to T1, T1 to Z. So what you can do, you can replace this T1 with directly Y. So you can assign this Y to Z directly, and then you can basically remove this, because it will become a dead code. So this is how you can do the optimization. All these are, remember, these are local optimization, because we are performing optimization inside a basic block. Here also you can perform the copy propagation analysis. Okay, this is your copy propagation analysis. Now this was your local optimization. Now let's see the global optimization. Of course it is not in the syllabus, but let me just tell you how to do the global optimization. So the global optimization, what it will do, global optimization means this complete control flow graph. You are doing optimization on this complete control flow graph, means between the basic blocks, you are doing the optimization. So what optimization you can do, see, in this basic block, this Y equal to 137. So what you can do here, actually you can apply the constant propagation. I told you constant propagation means you are assigning this constant to this variable to this variable. So what you can do, you can replace this Y with 137, similarly this Y with 137. So this is how you can do the constant propagation. But now you are doing the constant propagation among the basic blocks, between the basic blocks. So you can say this is global optimization, because now you are performing optimization on the complete CFG. This is just idea of local optimization, global optimization. Now we will study all these techniques: copy propagation, constant propagation, dead code elimination, okay, liveness analysis. All these analysis now we will see. So this is how you can do the global optimization. Anyway, now we will study something called local optimization, and in this local optimization the first technique that we will study is something called common sub expression elimination. So basically we don't want to compute the same thing again and again. That is the point. Common sub expression elimination. Okay, you don't want to compute the same thing again and again. This is the point. So for this code, let's assume you make 3 address. Of course, you don't have to make this thing. This is given to you. Of course, in the GATE exam, they are not going to ask you to write the 3 address code for this program. You can see this is a very hard thing. But here you can apply the constant propagation on this IR. So this is your IR, and this you will get after the this intermediate code generation stage. So this is what you will get. Your compiler will get this. So your optimization stage will get this input. This is the input for your compiler optimization stage. So now what you can do, if you apply common sub expression elimination. So this is an algorithm. This is a technique that you can apply. So this technique, what it will do, it will just try not to calculate the same thing again and again. So let's see here. Here you can see you are computing a plus b and you are putting this into T4. Now you can see after this and before this, here also you are computing a plus b and you are putting it into T5. But you can see in between these two statements, in between from here to here, you can see neither a is changing nor b is changing, neither T4 is changing. Any of these values is not changing. Okay, you can see any of these values is not changing. So what you can do, you don't have to calculate this again. You can replace this with direct temp4. So you can replace this with temp4. This is how. So this is called common sub expression elimination. Okay, this is how you can do. But remember, the point is basically that this is your statement, and after this statement and before this statement, you can see in between you are not changing, you are not assigning, you are not defining a, b and T4. You are not assigning them, you are not defining them, you are not changing them. So that's why you can do this common sub expression elimination, because still this a plus b will have the same value which is already in the T4, which you have already computed, and you have put it in, you have stored it into T4, so you can reuse it. So you can just directly replace it with T4. This is how you can do common sub expression elimination. Let's see something else. For example, you see here here you are putting 4 into temp 0. Okay, so okay, so what you are doing here, you are putting this 4 into temp 0. Here you are putting this 4 into temp 3. So here also what you can do, just see in between, is this temp 0 changing or not? You have to check it. Is this temp 0 changing in the between or not? So let's see temp 0 is changing or not. So I think temp 0 is not changing. So you can replace this also with temp 0, because this temp 0 is not changing. So this is how you can do the common sub expression elimination. Okay, so let's see this example. Let's see this example. Here you can see this temp4 you are assigning to the variable c, and here also this temp4 is being assigned to temp5, but in the between you are not changing. Actually this is copy propagation also. This is actually copy propagation. You are replacing it with c. This is actually copy propagation. Maybe the copy propagation may be the part of common sub expression elimination. So actually this is copy propagation. Anyway, let's see this. Let's see the definition of this common sub expression elimination. We will see this. So this is the definition, and this is the procedure. This is the definition and this is the procedure. In the GATE exam, in our syllabus we only have local optimization. So they will give you a small basic block. All the there will be no loop, there will be no conditional statement, there won't be anything, because you will be given a basic block. In our syllabus we have only local optimization. On that basic block you need to, they will ask you to apply common sub expression elimination. They will ask you, and they will ask you what will be the output of if you apply the common sub expression elimination, then what will be the output. Some programs will be given to you and you need to find which of them will be the correct output. Or they can ask you, they will give you a program and they will ask you to they will give you some different program, maybe program P1 and program P2, and they will ask you which technique you have applied from P1 to P2, which optimization technique you have applied. So these things they can ask you. So let's see the formal definition of common sub-expression elimination. So far we were only looking at the program and we were solving the question. Okay, but if we know the formal definition, then things will become very easy and we can do very easily all these things. So what is this common sub-expression elimination definition? The definition is this: if we have two variable assignments like this, you are assigning A OP B to V1. Okay, you are computing this expression and you are storing it into V1. And then some statements are there, and here also again you are computing this A OP B and you are assigning it into V2. But remember, in the between, in this between, okay, the values of V1, A and B, they should not change. Because if they are changing, then you cannot do this. If let's assume that you have this statement, you have this statement A equal to Y equal to A plus B. Now you are changing A. Let's assume you are changing A equal to A plus 2. And now if you have U equal to A plus B, you can see that now you cannot do, actually this expression and this expression now are different. Okay, these are now different because this value has changed in the middle. So now you can't do the common sub-expression elimination. So don't just directly do the common sub-expression elimination. The rule, the definition, the formal definition, the rule says that if you have this statement, A OP B is assigned to V1, A OP B is assigned to V2. In between, because this is a local optimization, remember, because this is a local optimization, so you have this statement, in between you will have a sequence. Because this is a basic block. In the basic block you won't have this type of loop. In the middle you can't go anywhere from the middle, so these things will not be there. So what you can say that between in these statements, if you are not changing value of A or value of B or value of V1, then what you can do, you can replace this A OP B with V1, because you don't have to compute it again. So this is how you can do. So this is called common sub-expression elimination. Okay, so this is how you can do the common sub-expression elimination, and this is in the GATE syllabus. Eliminates useless recalculation. You don't have to do the recalculation. Okay, so let's see. So now we will see something called copy propagation. What is this copy propagation? Let's see. So actually this is copy propagation. Here you can see I told you that you are assigning this variable to X and you are using this variable X here, but there is some again the same things are there in this middle part. Like, you should not change the value of X. You should not change the value of X, and you should not change the value of T1. Basically, the value of X and value of temp1, you should not change in this middle part. Then what you can do, you can replace this X with temp1. You can, like, this is how you can do. You can replace this occurrence of X with temp1. Okay, because you are assigning this temp1 into X. Now you can change this X in X by temp1, because in the middle you are not changing X, you are not changing temp1. So you can replace this X with temp1. Similarly, you can replace this X also with temp1, because you can see anywhere you are not changing X, you are not changing temp1. So this is how you can do the copy propagation. Now similarly here also you can apply the copy propagation. You are assigning a variable to A, and now this variable you are using here, and in the between you can see, in the between actually there is no statement. So anyway, but basically the in between you are not changing A, you are not changing temp3. So what you can do, you can replace this A with temp3. So this is how you can do. Okay, so similarly here you can see this is temp5. You are assigning this C to temp5, and you can see, wait a second, you are assigning this C to temp5, and yeah, right. So here this temp5 can be replaced with C. This temp5 can be replaced with C. Okay, because in the between you can see, in the middle statements you are not changing C, you are not changing temp5. This is how you can do the copy propagation. Okay, anyway, all these are examples of copy propagations you can do. You can go through these slides and you can check. Now let's see the formal definition of copy. So all these are many examples. Actually, he is doing again and again. Copy propagation he is doing again and again. Then this is how basically he is doing. Okay, everything, every time he is doing the copy propagation. Okay, again and again he is repeating the same procedure. Like this temp 0 you are assigning to temp 3. What you can do? You can replace this temp 0 with temp 3. Like, oh sorry, you can replace this temp 3 with temp 0, like that you should do. So I think, okay, yeah, he has done this, you can see. So you are assigning this temp 0 to temp 3. So what you can do here, this temp 3 you can replace with temp 0. So this is how you can do. You can replace them with temp 0. Anyway, this is your constant propagation. Okay, all these things are constant propagations. Sorry, copy propagation. Now let's see the definition of copy propagation, the formal definition of copy propagation. If we have a variable assignment, basically you are assigning v1 to v2, sorry, v2 to v1. You are assigning this v2 to v1. If we have a variable assignment, then as long as v1 and v2 are not reassigned or changed or defined, as I told you in the last class, assignment means definition. Okay, so as long as you are not as long as they are not reassigned, what you can do, you can replace this v1 with this v2. So you can replace this statement with this statement. You can replace this v1 with v2. Okay, so you can do these kind of things as long as they are not reassigned. Now we will see something called dead code elimination. This we have already seen in the last class also we have seen, and let's see it again. Just give me a minute. I have removed my headphones, so if you will be speaking, actually I won't be knowing. So you can just write in the chat box. Soumyadeep, how many type of local optimization are there? There are many. You can give your own local optimization. Okay, like there is no limit here. Research is going on. This is a very active area of research. Okay, do copy propagation really optimize the code? Yes, you will see actually when we do this copy propagation, then after this copy propagation we will apply something called dead code elimination. In the further examples in these slides I have given this. So we will see this. You will see this copy propagation is going to help us a lot, because after this copy propagation we will apply dead code elimination, and using by the help of this copy propagation the dead code elimination will become easy. And let me tell you, I have removed my headphone. It was just like I was uncomfortable with the headphones. So you will have to write in the chat box, and if you want to speak and you want to ask your doubt by speaking, then just write in the comment box that you need to speak, so that I can plug my headphones back. Okay, so Jairam, you for your question we will see examples just now. After 5 minutes we will see examples. And Soumyadeep, there are many local optimization. There is no limit here. When you do if you go and you do research in compiler design, then maybe you can give your own local optimization. Maybe you can give some optimization technique that can help the world, maybe. Okay, so there is no limit here, but some are very standard and those are in the GET syllabus. We will see those things. Like no one can ask you like how many will be there, 5, 10, that type of question you can't ask. So if v1 equal to 4, v2 equal to 4, then rewriting as v1 equal to v2 is it sub expression elimination or copy propagation? I think this is copy propagation writing. So like sometimes actually some of the definitions actually can intersect. You will see this thing, some of the definitions can intersect, like sometimes it won't be sometimes it is not possible to say whether they have done the copy propagation or whether they have done the constant propagation or whether they have done the sub expression elimination. Like I think there are some sometimes you can say, but I think sometimes you cannot say. I think that, but I will have to check it. Okay, so let's see the next thing. So dead code elimination, this we have already seen in the last class, and I told you dead code elimination means if you are not basically you are defining something, okay, you are defining some variable, and if you are not using this variable, if you are not using this variable again, if you are not using this, then this is a dead, dead, you can say assignment, this is a dead definition, or this is a dead variable. So you can remove this. For example, in this example you can see x, to x we are assigning temp1, to this x we are assigning temp1. Now you can just check, after this statement we are not using x, you can just check, after this statement we are not using x. So because we are not using x, so what we can do, we can remove it. Okay, we can remove this. This is dead code, so we can eliminate it because we are not using this x after this definition. Similarly here you can see this temp3, we are assigning this value 4 to temp3, and after this statement you can see we are not using temp3, we are not using this temp3. This definition we are not using anywhere, we are not using it anywhere. So that's why we can eliminate this also. And let me just I am repeating it third time, maybe third or fourth time, that use means like this. Here we are using A, here we are using B. In this statement we are not using C. So don't say that in this statement we are using C. No, this is not use. Use means we are reading value A, we are reading this value B. Means use means basically read. And definition, I told you, define means assignment, or assignment means write. All these things are same. So whenever I say you are using some variable, then basically I mean that you are reading that variable. Okay, like in this statement you are using variable A, you are using variable B, but you are defining variable C, you are not using variable C. Anyway, so here you can see this also, this is a dead code, you can eliminate. Similarly this is also dead code, you can eliminate, because you can see after this definition of A, this A is not being used anywhere. So you can repeat, you can delete this, you can delete this C, you can delete this also, because after this definition you are not using C anywhere. You can delete this, you can delete this also, because you are not using temp5 anywhere. After this definition you are not using temp5 anywhere, so you can delete it. You can delete this this also, because temp6 you are not using anywhere. After this definition, this is the definition, so you can delete it. So this is how you can do the dead code elimination. What is the definition of dead code elimination? An assignment to a variable v is called dead if the value of that assignment is never read anywhere. For example, in this example you can see this assignment, here you can see this here you can see this assignment to the variable temp6, this assignment, this definition of temp6, this assignment to temp6, we are not using this assignment, we are not using this definition anywhere. So this assignment, this definition will become dead, so you can delete it. So this is the definition of dead code. An assignment to a variable v is called dead if the value of that variable assignment is never read anywhere, is never used anywhere. So dead code elimination removes dead assignments from the intermediate representation. Now basically what we have to determine, if you want to apply this algorithm, let's assume you want to apply this algorithm, then what you need to determine? You need to determine which variable are dead, which variable are alive, which variable are dead and which variable are alive. This thing you need to thing you need to find out. Okay, once we find out this thing, then we can remove the dead statements, we can remove the dead assignments. Okay, so determining whether an assignment is dead depends on what variable is being assigned to and where it is being assigned to. So we will see this by example, it will be clear. Now what we will do, we will take some examples, and in all these examples we will apply common sub expression elimination, and we will apply copy propagation, we will apply dead code elimination, okay, in all these examples. So the common sub expression elimination basically eliminates the unnecessary statements, and basically unnecessary recalculations we are eliminating. Copy propagation basically I think Jairam asked this question that how this copy propagation is going to help us. So you can see this copy propagation will help you in identifying the dead code. So we will see this, okay, this after we apply this copy propagation, then if we apply the dead code elimination, then we will see that many statements will become dead. So we this is how this copy propagation is going to help us. And dead code elimination basically will remove the statements which are not used, which are no longer needed, because they are not used afterwards. So now, to get the maximum effect, we may have to apply these optimization numerous times. Actually there is no procedure here, like you can't say that apply this. Let me give you example. When you do grammar simplification, when you do this grammar simplification in the compiler design or in the TOC, you have this grammar simplification, you have a CFG. What you do, this CFG, first you remove the null production, okay, first you remove the null production, you remove them. Then what you do, then you remove the unit production, okay. Then what you do, you remove the useless symbols, the useless productions you remove, and then finally you will get simplified grammar. This is grammar simplification. Here you can see there is a procedure, like in this order you should apply. First you should do this null production elimination. After this you should do unit production elimination. After this you should do this useless symbol, useless production elimination. In this order you should do. Why do we have this order? Let me tell you. Because let's assume you do not do this order. Let's assume you do not want to apply in this order, and you want to do first, you want to do the unit production elimination. First you are applying the unit production elimination algorithm. Then the problem is that after you apply this unit production elimination algorithm, now if you apply the lambda production elimination algorithm, then again, because once you apply this algorithm, okay, once you apply this null production elimination algorithm, once you apply this, then you will see that again unit production will come in your code, again unit production will come. So what you will have to do, you will again have to apply this unit production elimination algorithm. Are you so you can see, when you apply in this order, then each algorithm you need to apply only once. Apply this once, apply this once, apply this once, and you will get your result. But if you do not follow this order, if you change this order, then you will have to apply the same algorithm. Maybe you will have to apply multiple times. Like if you do this first, then if you do this, then again unit productions will come, then again you will have to apply the unit production elimination. So you can see in this grammar simplification we have an order, in which order we can apply the algorithm. But in these optimizations actually there is no such thing as order. Like you can apply them in any order, and for the best, if you want to get the maximum benefit, then you will have to apply them again and again and again. Okay, so to get the maximum benefit, this is the line you can see. To get maximum effect, we may have to apply these optimizations numerous amount of times. Let's check this example, and on this example we will see all these three algorithms. Let's see. So this is your code. Now first you can see what is happening here. You can just see this is your common sub expression elimination. Why? Because here this is a star a, here also this is a star a, and in between this statement, in middle of these two statements, you are not changing a, you are not changing b. That is the condition. Remember that condition always. So now what you can do, you don't have to do this recalculation. What you can do, you can replace it with b. So this is how you will go. So common sub expression elimination you can apply, and you will get b. You will get this b. Okay, so this is how you can do. Now you can apply copy propagation. Now what you can do, you can apply copy propagation here. So now you apply the copy propagation. You can see this variable you are assigning to C, and here you are using C. And remember, between this statement and this statement, between these two statements, actually you are not changing B, you are not changing C, you are not changing B, you are not changing C. So what you can do, you can replace this C with B. So you can replace this C with B. So you have applied the copy propagation, and this is your result. This is your result after copy propagation. Now Jairam was asking, why do we do the copy propagation? So this is why we do the copy propagation, because after this copy propagation, now we can do the common sub expression elimination. Because here you can see, here you cannot do the, here you can see, here in these two statements actually you cannot do the common sub expression elimination, because here you have B plus C, here you have B plus B. So we cannot do the common sub expression elimination here. Okay, but once we apply the copy propagation, okay, then we will get this this basic block we will get. Now we can apply the common sub expression elimination. This B plus B, what we can do, this B plus B, wait a second. So this B plus B, what we can do, we have calculated it and we are storing it into D. So we can replace this B plus B with D, because you can see in between these two statements the value of B and the value of D is not changing. So that's why what we can do, we can apply the common sub expression elimination again. We can apply this algorithm again. So we will get this. Okay, so this is how you can do. Okay, so you can see sometimes you have to apply these algorithms again and again. So we will take more examples. Before we see more examples, before we take more examples of these three algorithms, these are the main important algorithms in our GATE syllabus. They have explicitly mentioned common sub expression elimination, liveness analysis. Liveness analysis is actually related to this dead code elimination algorithm. We will see this, how to do liveness analysis. This we will do. Okay, this we will see just right now. So before we go further, we can see some other type of local optimization, some other, like these local optimizations actually you may use in the UGC NET exam. In the UGC NET exam, they ask many times they ask questions from these optimizations. So anyway, I don't think in the GATE exam they are going to ask you questions from these optimizations, but we have these optimizations. Like we have something called arithmetic simplification. Like if you have some hard statement, hard operation, then you can replace it with some easy statement. For example, here you are multiplying with value 4. Maybe multiplication, like if you have studied the digital logic, then actually this multiplication is harder than the shift operation. The shift operation is very easy. In just one clock pulse you have counter, and in just you apply one clock pulse and it will be shifted. So you can, this shift operation is actually easier than the this multiplication operation. So your compiler knows this. Okay, even if you don't know this, but your compiler knows this. Okay, so this type of statement like multiplication with 4, when your statement when your compiler sees this type of statement, then what it can do, it can do the left shift with 2 time left shift. Okay, because you know when you do the 2 time left shift, then the value will be basically multiplied by 4. For example, let's assume this is your value 10. What is this? This is value 2. If you do 1 time left shift, then what you will get? You will get this. This is 1 time left shift. So basically when you do 1 time left shift, then the value is multiplied by 2. When you do 1 more time left shift, then the value is multiplied by again 2. So basically the value is multiplied by 4. Anyway, this is how you can do the arithmetic simplification. Replace hard operations with easy operation. This is how you can do. Okay, if they ask, like, I don't think in the GATE exam they are going to ask you these things, but if they give you, for example, from this you are getting this, what is the optimization that you have used? So you can just see that this is arithmetic simplification. You are replacing the hard operation with easy operation. You are changing the operation, but remember the semantic is not changing. You are not changing the semantic, you can see. Okay, you just need to multiply, so you can multiply like this. Anyway, this is arithmetic simplification, small simplifications. Okay, now constant folding. What is constant folding? Basically you can compute the value. For example, let's assume you have this statement, x equal to 4 into 5. Let's assume you have your program, you have written this statement in your program, then of course your compiler your compiler can very easily replace this 4 into 5 with x equal to 20. Okay, so that you don't have to calculate it again and again. Maybe this statement might be inside the loop. Maybe this statement is inside the loop. So every time the loop will run, you will have to multiply it. So what you can do, your compiler can just replace it with 20 at the compile time. Now when you run this loop, then you don't have to do the multiplication again and again. So this is called constant folding. Evaluate expressions at compile time if they have constant value. This is a very simple definition. So this is your constant folding. Now we will see how to implement local optimization. What do we mean by implementing local optimization? Let me see some doubts. If anyone has any doubt right now, let me see. Constant propagation, one example. Series we will take examples of constant propagation. Right now our focus is on these three techniques: copy propagation, dead code elimination, and common sub expression elimination. We will take examples of constant this propagation also. Okay, don't worry. Next, others is saying a equal to temp1, b equal to temp1. Sir, both common sub expression and copy propagation will work here. So as I told you, I will have to check it because are these techniques mutually exclusive? This I will have to check whether these techniques are mutually exclusive or not. Okay, maybe these techniques are not mutually exclusive. Some intersection could be there. Sometimes you can't say whether they have applied the constant propagation or whether they have done the this common sub expression elimination. I will have to check this. I will tell you tomorrow. So Indranil is saying this constant folding. This is very simple. Constant folding is just saying that if you have this type of statement, let's assume x equal to 4 into 5, then at compile time what you can do, you can replace this 4 into 5 with directly 20, because 4 into 5 means 20. So at compile time your compiler can replace this 4 into 5 with 20, so that at runtime you don't have to calculate it again and again. Okay, so this is your constant folding. Constant folding means evaluate expressions at compile time if they have constant value. So you can see this expression has constant values, so you can evaluate this expression at compile time. So this is how you can do. Okay, let's see this implementing local optimization. So here actually we will see how the algorithm we will do. So far we have not seen algorithm, remember. So far we have seen the definition, so far we have seen the idea, but we have not seen the algorithm so far. Now we will see how algorithm will do all these things, how algorithm will remove the dead code, how algorithm will remove the code, common sub expression, all these things. Okay, so algorithmically we will see. So let's talk about this thing. So actually when you want to do this dead code elimination, this is your purpose, dead code elimination. But before you do this dead code elimination, you need to analyze the program, you need to analyze the program text, and this analysis which will help you in your dead code elimination, this analysis is called liveness analysis. So remember, this is an analysis, liveness analysis. This analysis will tell you at what point of program, okay, which variable is alive, which variable is dead. So this liveness analysis will tell you that. Okay, and once this liveness analysis will tell you which variable is alive, which variable is dead, at what point, at every statement, at every instruction, this liveness analysis is going to give you the set of live variable, set of dead variable. So after this liveness analysis, you can apply the dead code elimination. So remember, this is a technique, and this analysis is going to help you in this technique. Similarly, this available expression is an analysis. Okay, you do some analysis, this is an analysis, and this analysis will help you in your common sub expression elimination. So this is what you want to do. You want to eliminate common sub expressions, but before doing this you first have to find out which are the common sub expression and all these things. So for that you have this analysis. This analysis will help you in common sub expression elimination. Remember, actually these analyses are more general than these things. For example, this liveness analysis can be used in many other areas also. Maybe you have some other code optimization technique, there also you can use this analysis. Okay, similarly maybe you have some other optimization technique, there also you can make use of this available expression analysis. So these things are more general, but they will help you in these optimization techniques. So let's see. So first we will see something called available expression analysis. This we will see how to do this analysis, available expression analysis, and after this we will see how this analysis will help us in common sub expression elimination. So you can see both common sub expression elimination and copy propagation, actually both of them, this CSE and this copy propagation, they both depend on the analysis called available expression analysis. So first we will do this, and you can see many different optimization techniques can use or can make use of this analysis. Now, so what is the definition of available expression? What is the definition of available expression? So this is the definition. An expression is called available. An expression is called if some variable in the program holds the value of that expression. Okay, so with the examples it will be clear, don't worry. And now in the common sub expression elimination we will use it. In the common sub expression elimination we replace an available expression by the variable holding its value. So with the example it will be clear. And in the copy propagation we replace the use of a variable by the available expression it holds. So let's with examples all these things will be clear. So first let's try to do the available expression analysis. So initially no expression is available. Of course, when you begin the program, initially no expression is available. Okay, now let's assume that this is your first statement. Let's assume this is your statement. So before this statement you have some available expressions, and then you have this statement a equal to b plus b. So after this, what are the available expressions? So after this statement, when we execute this statement, then now this a equal to b plus c, this will become available expression. This a equal to b plus c, this will become available expression, and any expression that is holding a, that will be invalidated. So okay, let's take example and it will be clear. So on this example now we will do the available expression analysis. After this example we will again recheck the definition. So let's see this available expressions. On this example, remember I am not going to do the common sub expression and elimination. On this example I am going to perform the available expression analysis, and using that available expression analysis I can apply many code optimization algorithms like CSE and copy propagation. So initially nothing is available. You can see initially this is your set of available expressions. After this expression, this is your set of available expressions, a equal to b. This is your set of available expressions. Now after this, here you can see this is your available expression, this is also your available expression. So after this statement, now this is your set of available expressions. Okay, after this next statement, this is your set of available expression, because now this is available expression, this is available expression, this is available expression at this point of time. So you can say that at this point of time this is your set of available expressions. Okay, now so after this statement, what is your set of available expression? This is, because now this is available, this is available, this is available, this is available. Now the important thing is coming. Now after this statement, what will be available? See, after this statement, this definitely will be available, but now after this statement, what is happening? After this statement, this value of d you are reassigning. This value of d you are reassigning. So now this expression will become unavailable, because now this is unavailable, right? Because the value of d you have already reassigned. The value of d you have already reassigned. So anyway, this expression is not going to be used again. From now onwards, only this expression will be used. So this is the important point here. This is the only important point. Basically, when you have this type of statement, let's assume you have this type of statement. Before this statement, let's assume this is your some set of available expressions. Then after this statement, what will be the set of available expression? In this set, you include this set, this expression, of course, because this expression is definitely available at this point of time. So you include it, but remove those expressions which include d. If there is an expression which include d, for example, let's assume if there is this type of expression also, then you can remove this also, because now this is not available. Because now this is not available, because now the value of d has changed. So that's why this expression is not available now, because the value of d has changed. Similarly, if you have this type of statement, a equal to b plus d equal to a plus b, then this is also not available. Okay, because now the value of d has changed. This is your available expression analysis. So after this statement, you can see that after this statement, this expression now this is not available now, but this is available. After this statement, this is available. So this is your final answer. This is your available expression analysis. Anyone has any doubt, then you can ask right now. Anyone has any doubt in this available expression analysis? So let me tell you just one more time, let me tell you that if you have this type of statement, let's assume you have this type of statement, a equal to b plus c. This statement you have. Before this statement, let's assume this is your set of available expressions. This is your set of, let me call it s. Let me call it s. S in. Let me call it s in. Then what will be s out? Because this is your set of available expressions before this expression, before executing this expression. After executing this expression, the set of available expression, what it will become? In this s in, you will definitely include this expression. Let's call it this expression I. Let's call this expression I. So you will definitely include I, because now this is definitely available. But you will remove those expressions from this s in. You will remove those expressions which has a. For example, if you have this type of expression, let's assume a equal to d plus e, then this will be removed now. Similarly, if you have d equal to a plus e, then this will also be removed. Basically, anywhere if you see this a, then that will be removed, because now the value of a has changed. So all these expressions are now not available. Okay, so that's why this is how your available expression analysis will work. This is a very easy thing, I think. Anyone has any doubt, then you can ask. You should ask right now. This is a very important analysis. We have only, I think in the GATE syllabus, we only have two analysis. Available expression analysis, because it will help us in the copy propagation, it will help us in the constant sub-expression elimination. And another analysis that we have is liveness analysis, because that will help us in the dead code elimination, and that is your complete GATE syllabus. So today I am just covering the mentioned topic, like they have explicitly mentioned all the topics like local optimization, common sub-expression elimination, liveness analysis. All these topics I am covering today. So you should ask if you have any doubt. This is your available expression analysis. Very easily you can do this. No one has any doubt? Okay. Then let's see again. So now you have done the, see right now at this point of time, you have done the so at this point of time you have done the complete available expression analysis. Now what you can do, using this analysis, now you can apply the common sub-expression elimination. Actually, after this analysis, the common sub-expression analysis will become very easy. So what you do, you just go from top to bottom, you just keep on going on. See here you can see when you come to this statement, at this point of time the available expression is a assigned b. This is available expression. So what you can do, you can replace this what I am saying this. So okay, I think the copy propagation and common sub-expression analysis has this difference. Okay, let me tell you this difference between copy propagation and common sub-expression analysis. In copy propagation, we do this. We are assigning V1 to V2, and let's assume V3 to V1. Let's assume this we have. Let's assume this we have. In copy propagation, we do this because we are assigning V2 to V1 and V1 to V3, so we can directly assign V2 to V3. This is your copy propagation. In some common sub-expression analysis,